I am going to talk about capturing the uncertainty in machine learning, focused on some of the geoscience applications. The work is as a result of collaboration with quite a few of my colleagues that have contributed, and I share with you some of the findings here. But just to begin with, I quite like to start with some intro and the fact that machine learning obviously at this moment is quite a hype, and a lot of attractions with researchers around the world. But one could argue that machine learning has been around for decades. In fact, you could argue that it has been around for centuries. At the heart of machine learning are the concepts of numerical analysis, especially if we go to the work of least squares. And since we are talking about capturing uncertainty, then one could not basically ignore the work of Thomas Bayes and the foundation that he built for the mathematical theory of probability, which also is basically the foundation for a huge amount of work that is currently going on at this moment for implementing the same principles on deep learning and machine learning models. So this is effectively a kind of a schematic time frame starting from 1763, and of course many names are not depicted here. Some I quite like reading and learning their work. Of course, the Legendre, the father of the least squares, this is the only picture left of him. Up to I think 50 years ago, he was confused. His photo, the one photo of him was confused with a French politician, but later on, people discovered that this is the real legend behind the mathematician legend, basically, and quite an angry-looking chap. And then the work of Markov and the famous Markov chain, and we know the effect of this on stochastic processes in mathematics, and of course the father of artificial intelligence, Alan Turing, and the paper that he wrote at the foundation of learning a machine in the 50s. So hopefully with this kind of background, now we come towards modern time. And again, I said, going back a couple of decades ago, in the 80s, people started to already talk about recurrent neural network, the type of neural network which are the ancestors for what we know today as LSTMs, or long short-term type neural network, kind of have a memory to remember some temporal relationship in time series primarily, but people implemented in other applications, and support vector machines before really neural networks and deep learning becoming a thing. People used to implement and utilize support vector machines primarily. Again, the foundation was built in the 80s and 90s by some Russian mathematician. And then going forward in the beginning of this century, really we started to see the application of deep learning, and that was powered by the availability of the compute. But since I want to bring the concept of uncertainty into geoscience, again, as an indication of where we are in geoscience, I would like to put also one paper that made an impact on me personally and many geoscientists of my generation in this field. The paper that Boulan and Omre, by the way, Norwegian, I believe they are from University of Bergen or Stavanger. Can't remember. One is now working for Equinor. Nonetheless, their work on formulating inversion for seismic data in a probabilistic fashion was groundbreaking, in my opinion, and it was only published in 2003. So while the rest of the world pretty much was consumed with advancing deep learning, we were still working with conventional methods in seismic data. And it's only recently that we are, at least in the geoscience community, we are trying to implement machine learning more and more in practice. And right now there is a huge amount of paper being published, but of course we had COVID hitting us, and then oil and gas. At some point the price went negative. But it is looking a little bit better these days. But it's not only the application for the oil and gas industry, it is for the entire subsurface domain. So it's effectively characterizing the subsurface, which has implication for renewable storage of CO2 and other green applications, if you like. So now, when it comes to capturing uncertainty in machine learning, of course, we know that the outcome of machine learning is typically categorized in two types: classification and regression. And then for these things, uncertainty may mean a different thing. So for classification is the confidence of that class, and then the regression is basically the mean and the standard variation around that mean for the predicted outcome. And there are kind of different things. I'm not going to show two formulas or anything. We stay high level, and the mathematics behind these things are pretty advanced and to some degree above my head, but in terms of implementation and in practice, people typically, and from kind of easy to more complex, start from top to the bottom here. Ensembles are where you train multiple models and create an ensemble basically with different initialization, and then variational inference and stochastic weight averaging are both where people use the Bayes and the Bayesian formulation to kind of either formulate the neural network in an optimization problem or some form of averaging in the stochastic gradient descent process, which is the case for stochastic weighted averaging. So these are the typical approaches that are in place today. So I kind of try and demonstrate it a little bit more with some pictures. When we talk about dropout, which is the variational inference here, effectively, if you have a fully connected network where the neurons are connected all together, after dropout, effectively you kill or disable some of the neurons at your inference time. And this allows you to create multiple outputs, which subsequently allows one to create the distribution around the prediction, which means we can capture the uncertainty. Effectively, what people did for what is known as a concrete dropout was to make the dropout parameter how many neurons you want to kill effectively at each iteration, to make that parameter adaptive to a specific data set, and that is known as a concrete dropout method. Ensemble, again pictorially, is where we create different models completely independently, and they typically have different initializations, sometimes with different architecture, or sometimes with different model types even. And you create a distribution of the outcome, which allows you to create the mean and the variance around the prediction. And again, to show everything in perhaps one picture, and and bring the Bayesian concept into the picture is one has to look at the posterior distribution, which is the distribution of the effectively your predictions, and again schematically you can see that the deep ensembles are at different peaks of these highly non-linear type problem. So you have multiple possible solutions, and deep ensembles are trying to capture each one at a time, and you come up with an outcome at the end. And then the stochastic averaging is focus on one distribution, and then the concrete dropout is in practice capturing a little bit more of the variation. So you have again in theory a better chance to capture the uncertainty more accurately. But then also there I should have had the reference here, but I think it was the reference was mentioned in the earlier slide. But there's also a nice way of splitting the uncertainty to two types, what is known as aleatoric uncertainty and epistemic uncertainty. So aleatoric is the uncertainty in the measurement. So can we reduce such uncertainty if we had better data? So if you look at this image with the car and the pavement and pedestrians, and you can see that aleatoric uncertainty at around here is high. So potentially, does this indicate that a better, higher resolution image can reduce this uncertainty and the misclassification at this area? Similarly, epistemic uncertainty, where it's effectively pointing to the uncertainty in the model. You see that in maybe an area that we can look at is in the car, and just under the car where it's pretty close to the edge, could be an edge effect or not. And effectively here you see that the model is pointing to something uncertain. So again, is this something that the model doesn't understand about our data? So could it be that if we had more pictures, perhaps from different angles, or something that could reduce this type of uncertainty that we have in the result? So things that you can infer from the observations in these type of attributes. So if I go effectively, what we do now, we move to the geoscience applications, and we'll have three examples. 1D property predictions, which is implementing dropout method to capture the uncertainty. So and then we will have two more examples where we implement the ensemble and another method of the and another example also in 3D, which we compare different types of methods in capturing the uncertainty. So beginning with 1D and beginning with perhaps the most straightforward approach of dropout. Just to give you a background, this is when we deal with well data, so the measurements that are along the wellbore as we drill in the subsurface, and effectively these are physical measurements, measurements such as sonic velocity or shear sonics or density and alike. And there are typically good physical relationships between these parameters that people have derived based on measurements, and also based on measurements in the lab that you can utilize and use in your workflow. So some are reported here, and these are often used in the workflow. So really the objective is that if we have a wide range of data, in fact, we do have in Norway, as an example, the whole Norwegian NCS data set in available via Discos. So if you have all this data, can we use a data-driven method to predict these properties using the measurements that we have instead of using experimental relationships? So with that, effectively, that's where you can implement their neural network, and effectively you can use the conventional neural network. But also, we mentioned earlier in intro slides that there are types of neural networks that you can capture the temporal behavior in the logs. And we know that the geology, there is some relationships as you go down in depth in the subsurface. So there are cases where the layers or the lithology units remain blocky, or there is some progradation like this, or retrogradation like this, or the opposing directions. So this type of, although I'm not a geologist, but these type of behaviors are well known from the domain expert point of view. And the idea is, if we know there is a relationship from one sample to the next, can we implement it in the model? And the answer is yes. This is the work we did with NAM-FAM. And the idea was to implement the so-called LSTMs, those which have a memory to remember what's happening between the previous sample and the existing sample. Again, a schematic architecture shown here, more detail in the paper. And then once you have it, you can predict. So in this case, the predictions are shown in red, and then the true answer is shown in black. And then if we use the experimental formula, it is shown in green. And of course, these are the areas that are chosen where the experimental kind of approaches have pretty much failed. But we see that the neural networks that are learning the behavior from the existing data are capturing the relationship better. And typically these things are also QC'd in what is known as crossplot domain. So here is a crossplot of the estimated sonic versus density on the test wells, so completely blind wells. And then the same crossplot, sonic versus density for the measured data. So the idea is the comparison of the right versus left, and overall we have to have the right sort of scatter in the crossplot domain. And it looks like that it's doing the right job on these completely blind wells. So now another example is where we want to do 3D proper. So those examples, as you saw, they were all 1D measurements. And now we are going to basically predict in 3D. And in this case, the uncertainty are captured via the ensemble method. So when we say 3D, how do we move to 3D? Again, is to use the advantage of the vast amount of data that is available when it is available. And for example, in this case, and also the key is to connect the 1D world from well data to the 3D world of 3D seismic data sets. So here you see that there is an outline of a 3D seismic survey in white, and the wells that are within this seismic block shown as little circles. So what the job is now is to train the neural network to find the mapping function that trains from the wiggles around each well to the desired property at the well location. So seismic wiggles are recorded indirectly from the surface, and reservoir properties are recorded within the wellbore, and now we can just use the neural network to connect these two. And once you find the mapping function to go from the wiggles to the properties, then you can do your inference over the entire volume. And there you have a 3D picture of the property of interest. So here is an example where we use 11 wells for the training, but you can see that generally and regionally, you can have a lot more wells to prepare these wells for training, for the information that you might be missing within these wells. So effectively, you can still use all the regional wells to have the training of these 11 wells as complete and as robust as possible. So this is a picture of the seismic, and typically the seismic obviously carry a lot of information about the structure, and you can see all these formations that are very familiar for the geologists. But then still nobody can go and comfortably drill a well to find the natural resources in the subsurface by only looking at this. That is the motivation why we convert these pictures to 3D properties using the well data. And then once you do that, first of all, you QC again that you are predicting it correctly. So here is the prediction at the blind well in blue and our prediction in red, and the uncertainty that is obtained via ensemble. So we want to make sure that these uncertainty bounds are not too wild and within range. And you can see, for example, an example here is that this layer that I indicate by the mouse could be a thin layer that is of importance, whether from the drilling point of view or from the reservoir point of view. But the prediction of the neural network is kind of missing it. But when we capture the uncertainty, we see that the upper bound of the uncertainty is overall capturing that trend. And that is the sort of useful information that we must consider when interpreting the outcome of these models. And again, looking at the result in the cross-plot domain and looking at the metric and making sure the predictions are pretty compressed around the main diagonal. And okay, this is one property that I showed, what is known as velocity ratio, or sonic and shear velocity ratio. It is typically a good indicator of the reservoir and also the porosity. Again, you can see the uncertainty bounds and the prediction. Now here you see a little bit of a wider scatter, and that is also represented with the wider uncertainty bounds in the predictions. And once you are comfortable with your predictions, you can, as mentioned, you can do the inference over the entire volume, and you have the picture of the subsurface now with the properties, with the physical properties, which is a lot more useful for characterizing the subsurface and knowing the property of each layer in the subsurface. So these are the impedance, velocity, lithology, and porosity properties, and you can look at it at different directions. You can see these injectite bodies also captured quite nicely with higher porosity values. And again, it's all about QCing, bringing that domain expertise and interpreting what we observe and matching it with the information that we have. Well, so the actual machine learning is one thing, but the coupling that with the domain expertise and making sure that we have the right outcome is key to success. utilizing the value from these models and workflows. So finally, I finished with one last study, a recent study, and on a paper that is currently undergoing review for publication, where we compare in a 3D interpretation method the three of the uncertainty estimation and calibration methods that I mentioned. Oops, yeah, so just to give you an idea, in the past, or say in the 90s, when people had these type of seismic data, we used to compute lots of different attributes, so that those attributes can give us an idea of some interesting features in these images. So you can see that these faults are pretty, well, if you know what you're looking for, it is quite distinctive by our human eyes, but there are certain attributes that they highlight them better, like these attributes here. And these were kind of the practice and part of the workflow in those days. But now, again, the idea is whether we can use data-driven methods. And of course, it is possible, but to train these neural networks, we need to manually label the faults. And that labeling task is quite time-consuming, and one could say that, oh, if I spend the time to label, then I might as well label the whole thing. And there are, again, different sides of the argument to such a statement, but at least there is one solution that is definitely a huge advancement, and that is basically implementing synthetic data. In this case, we know how to model the subsurface, and by such a workflow, we can place these faults, and that allows us to train the machine learning in a supervised manner and knowing exactly where these fault planes are. So you have this in input and you have the fault planes and the target, and you can create millions of these images and train them, and that gives you a model that is pre-trained and you can apply it on real data sets going forward. And then once you have that, again, by means of by the means that I mentioned earlier, whether it's ensemble or dropout or swag, stochastic weighted averaging, you can capture the uncertainty. And you can look at different types of uncertainty. So here, there is a fault, and the fault has a shape of a disk. And what we're looking at is the estimated aleatoric uncertainty, the uncertainty that is data dependent. And you can see that its uncertainty is higher around the edges of this fault. And it is, again, it's something that we can relate to. We know that at the boundary of these faults, it is always a question mark when the fault finishes, and this is what appears to be picked up by the model of higher uncertainty region, and we can compare different methods, as I mentioned, the stochastic weighted averaging, dropout, and ensemble versus a deterministic method, basically. And you can see the fault mask, the target, basically, the fault probability, which looks pretty much similar, and the total uncertainty, aleatoric and epistemic. And you can see that generally we see the same picture, while what stands out perhaps is that the swag is maybe underestimating the epistemic uncertainty, and the aleatoric uncertainty is similar amongst the three methods. can look at on real case against similar observation, which we have seen in the synthetic case. We see it on the real data case. You see that swag behavior versus the other methods. And of course, the prediction power of these things are still relatively similar because they are using the same network architecture. Nonetheless, from the practical point of view, one could argue that perhaps dropout offers the fastest and most efficient method. And then following that is perhaps swag and ensemble, giving the complex computational complexities. But to finish off why we spend this time to look at these things, I think if there is one picture to explain this, it could be this one on the, at least in the example I mentioned here, is that we estimate these fault probabilities, and from these you can extract fault surfaces. But the key of and the value behind looking at these things in a probabilistic manner is where you have different realization of the outcome. So you see 3 realization of the estimated fault planes of this method, in this case using the concrete dropout. And you can see, for example, this fault plane here appears, disappears, and appears. In this case, doesn't exist, and here there is a more continuous kind of feature to it. And this could have huge implication when you take these models and this knowledge to the next level, which is related to the reservoir simulation or management and the connectivity of the reservoir effectively. This could be a barrier or can change really the behavior on what might come next in the understanding of the reservoir and the optimization of production if it is related to the hydrocarbons. So to finish, I think machine learning, we know it's all about efficiency, but I think what I would like to say, and I have tried to show you with examples here, are that it can offer more if we capture the uncertainty, and it is this feature that can facilitate the interaction between the practitioners and the machine. That's where you see the high uncertain output. You as a practitioner can improve the, first of all, understand why it is uncertain. Second, and then potentially go back and maybe improve your training data or edit your input data and retrain and eventually get a better outcome of your model. And that could be a very interesting practical workflow of such interaction.